Good morning. This is Dr. Madhusudana Reddy, PVR with Kavali. This video session for Thought BTech Second Sem EE students. Subject is Design of Photovoltaic Systems. Unit 1. Already I covered five video sessions. Now this is the sixth video session. I will continue with this. Just a minute. In this, I'll clarify about what is the fill factor and cells in series. So these two concepts will cover in this video session. So first of all, I'll explain about this. What is the fill? Just I'll go through this a little bit of more explanation. Here, this is about, and this is about IV. This is about I, and this is about V. And this is about the IV characteristics. So, for example, in generally, these IV characteristics are represented like this. IV characteristics are represented like this. Okay. So when these IV characteristics are like this, so this is the representation of ISC when or not is equal to 0, or resistance of load should be equal to 0. This is about VOC when or not is equal to infinity. Okay, infinity. Fine. So, for example, if I change this some value of this, then what's happened? So this indicated as a load line. So this is 1 by R naught. It should be equal to I by V. Delta I by delta V. Okay, fine. You understood that? So this is the middle. It's the worst characteristics of this. So then what's happened here? For example, it is a power curve. See here. So this is about VM, and this is about IM. Okay, fine. And this is the area for this. This is the area for this, and this is the area for this. For example, you'll see here. So this is about you are having. Sorry. So this is about VM at this, and this is about IM. You are having. Okay. For example, you'll pick up as a color will be changed. For example, see here, and this is about the complete load. Okay, and see here, this is about only area for this. It's okay. Let me go for it here. This is the area. This is the area, and you'll come back. I'll come back here. So P in is equal to L into area. Yes or no? If these parameters are changes, then what's happened is area increases. So this is the one of the characteristics, ideal characteristics. Okay. If you see here, when you consider this and this, you'll consider area is less. Then what about P in is also increases, and here also P in decreases. So then what about the efficiency? Whatever the efficiency increases, the efficiency will decreases. So what is the fill? What is the fill factor? It is the quality or ability of a PV cell. It is the ability of a PV cell. Okay. What is that? Fill factor is equal to, okay, so maximum power divided by input power. Okay, input. So what is the maximum power is nothing but, okay. So for example, not maximum power. So this is about, sorry for a maximum power. It is not a maximum power. It is the ratio of, it is the ratio of, this is the ratio of, fill factor is the ratio of, fill factor is ratio of VOC into ISC divided by VM into IM. VM into IM. Okay. If this area increases, so then it will go as this. RPM divided by VM. Sorry for this also. Factor. Fill factor is equal to, fill factor is equal to, here you'll get to this PM divided by PM. PM divided by, or VOC into ISC. Okay. If this area increases, this output power or Pin is also. Pin is also. Okay. So if area increases, then it will be changes. But I'll explain here. Let me go for here. So what is the fill factor? I'll go for it. What is the fill factor? Fill factor is actually a figure of merit for the PV cell. Like already you learn in your basic fundamentals. Quality factor of a coil. What is the quality factor? Is the ability of a coil. It is an integer number. So it tells how good or how bad PV cell is actual. It is actually ratio. Now before tell the what is the ratio, let us get it into a much more initial manner. Now we see that IV catch of PV cell. Now let me have a projection of along the perpendicular to the voltage axis and the projection of ISC perpendicular to I-axis and the points VOC, ISC point as shown here. Okay, see here. So fill factor is nothing but VM into IM divided by VOC into ISC. For example, already I told you, this is the bad characteristic. This is about the VI, this is about the bad characteristics. Okay, let me go over here. Not that. So this is about this one. So a particular line is there now. I'll go for it. I'll show that line. Yes. So this line. This line is the IV characteristics of the bad characteristics. So this is the area and this is the area, bad characteristics. For example, this is okay, good. This is okay, good. And at this, you compare with this. So for example, as per your data sheet, what is the VMIM and what is the VOC ISC? From this 30.18 into 7.96 by 36, what is the fill factor? 0.72 is the fill factor. So it is the ability of a coil. What is the fill factor? It is the ability of a coil. VOC ISC, this rectangle. Here now, let me fill up this area, represent this maximum possible voltage and the maximum current that theoretically possible. So VOC ISC is theoretically possible, but not practically possible. PV cell, but this point will never be reached. Now, particular characteristics of maximum power point is given as VM and IM, which cover a rectangular area like this. Okay. So observe that when the R series non-identically removed and become series, that okay, factor is actually a figure of merit. Tells how. So this VOC ISC would be the peak power, a weak power of such an ideal cell, but with an happens this more practical cell. So now the definition of the peak factor comes as this. It is the ratio of maximum power to the actual ideal case of the power. So this is about the ideal case of the power. This is about the ideal case of the power. Okay, ideal case of the power. But what is the actual power? So this is about the actual power. So the ratio of actual power to the ideal case of the power, which indicates the fill factor. Based on the fill factor, we can understand that performance of the cell. So this fill factor is always lies between 0 to 1. We never have the 0, we never have the 1 value. It's always more than the 0 and always less than the 1 value. Okay, so always less than the 1 value. See here. So based on these values, we pick up the based on these values, we evaluated the fill factor. What is the fill factor of our cell? 0.72. 0.7. So now 0.72 is a reasonable panel available in the market, but the fill factor is 0.5. 0.5 is a very bad cell. If the fill factor is 0.8 to 0.8, is a very good cell. So based on this fill factor, everyone can understood that the performance of the PV cell. If the fill factor is good, the PV cell condition is good. The PV cell fill factor is bad, less value, lower value, then the PV cell performance is very, very bad. So that is the fill factor of the is generally calculated to measure the quality or the goodness of the PV cell. Next, we'll come back to cells in series. So first of all, why we need the cells in series? Generally, always we need to increase the power. Each and every cell will contain very small magnitude of the power. With a single cell or with a single module, we cannot get into the application. We cannot connect the solar cells. A single cell or single module cannot be useful for an application. As an application, we want to convert. We always connect these cells either in series or parallel, which depends on the increase in the voltage magnitude or increase in the current magnitude. So everyone knows that already we learn in AC fundamentals. What is the series connection characteristics? In series connection, the current should be same, but the voltages are additive in nature. If you need more voltage, we always connect the cells in series. If you need more current, always connected in parallel. So that is happening. So PV cells of the solar cell, it has to be useful so that it can be made used in power application, need to be enhanced at the power. So which means the voltage has to be higher, much higher than 0.6 volts of each and every cell, but the current has to be higher. So for this, PV cells, many PV cells need to be connected in series or parallel. Combination of both arrive at a module. Now, can this done? We can connect PV cells in series directly. We can connect PV cells in parallel directly. So what happens if one set of PV cells have different characteristics? While discussing here, there are two types of cells are available. Identical characteristics and non-identical VI characteristics. If identical IV characteristics are there, no problem. It's very good. If non-identical IV characteristics, there must be so much of problems. Okay. But we'll see here how we are connecting the cells in series. So one cell positive terminal, every cell containing the two terminals, positive terminal, negative terminal, positive terminal, negative terminal. One cell positive terminal connected to other cell negative terminal, like that you can make many number of cells in series. Next, this plus connected to other cell. Same other cell plus is connected to other cell minus. In that way, in such a way, we can make many number of cells in series. So I hope you understood that what is the series connection. Here we taken only two cells. Two cells are connected in series. That's why the second cell plus is connected to the first cell minus, and first cell plus and second cell minus is taken as connected to the load. And these two cells are carries the same current, but these two cells having the different voltages VT1 and VT2, and you need this total voltage is equal to VT1 plus VT2. So that is about this connecting in cells in series. So now we'll see here, these are all the characteristics already I told you. But we can understood that how we are made this as an equivalent. So this is about the photo mode. Next, when you connect this equivalent model, we should remove our resistance of series and shunt and series. Then that equivalent is modified. And with the help of this, we connect these two cells in series. Okay, what's happened, we will see in the class with the help of a